billions and billions of dangerous high-energy particles reach the Earth from the Sun every day, sometimes several times a day. Such solar winds can cause planet-wide outages and even be fatal to us and every other living organism on this planet. But still, here we are. The question is, how? The answer is the Earth's magnetic field. As you can see, this field deflects a large portion of the harmful radiation before it reaches the surface. But how does the Earth have a magnetic field around it naturally? As we know, the Earth's crust contains oceans of molten rock moving around. These molten rocks contain charged particles in them, causing a flow of charge. This flow of charge, or what we call electric current, creates a magnetic field around the Earth, forming the magnetosphere. This phenomenon can be simplified as Ørsted's law. The Danish physicist Hans Christian Ørsted in 1820 found that the needle of a compass next to a wire carrying current turns so that the needle is perpendicular to the wire. From this experiment, he concluded that when a steady electric current passes through a wire, it creates a magnetic field around it. The French physicist Jean-Baptiste Biot and Félix Savart created what is called the Biot-Savart Law, explaining this relation between the electric and the magnetic field. The Biot-Savart Law is an equation describing the magnetic field generated by a constant electric current, as per which the magnitude, the direction, the length, and the proximity of an electric current relates to the magnetic field generated by that current. To explain the Biot-Savart Law, let's consider a finite conductor, XY, which is carrying a current I, which in turn creates a magnetic field around it, as you can see. In this conductor, consider an infinitesimally small element called dl in this wire. Now consider a point P at distance r from the element and theta as the angle between them and the axis of the element at that point. As per the Biot-Savart law, the magnetic field at this point P due to this current element, that is small dB, is proportional to the current I and directly proportional to the element length dl and inversely proportional to the square of the distance r. Replacing the proportionality with the proportionality constant, we get this relation which holds true when the medium is a vacuum. The proportionality constant has the value of 10 to the power -7 Tesla meters per ampere. Here, mu naught is the permeability of free space or vacuum. Getting back to the image and solving for the cross products, we get the equation for the magnitude of the magnetic field at point P due to the element dl. Another law that we have to understand is Coulomb's law, which states that the force of attraction or repulsion between two charged objects is directly proportional to the product of their charges and inversely proportional to the square of the distance between them. This force acts along the line joining the two charges, considered to be point charges. So we get this equation where F is the magnitude of force between the two charges, Q1 and Q2 are the two charges, R is the distance between them, and epsilon 0 is the permittivity of the free space or vacuum. Now, both the Biot-Savart law for magnetic field and Coulomb's law for electrostatic fields have certain similarities and certain differences. Since both depend inversely on the square of the distance from the source to the point of interest, both are long-range forces and both also obey the principle of superposition of fields. Another difference is that the electrostatic field is being produced by a scalar source. That is, we are only concerned with the magnitude of electrical charge, not the direction of its movement. While the magnetic field is produced by a vector source, that is IDL, since here the current also has a direction and DL also has an orientation. In addition, the electrostatic field is along the displacement vector joining the source and the field point. But the magnetic field is perpendicular to the plane containing the displacement vector and the current element. And lastly, we understand that the Biot-Savart law has an angle dependence which is absent from Coulomb's law. That is, the angle that the point vector makes with the axis of the conductor is important for Biot-Savart's law but is not a concern for Coulomb's law. Now that we are clear about the magnitude of magnetic field at any point there is a current carrying conductor, what happens to a magnetic field at a point when the current is traveling in a circular loop? Curious? Stay tuned. Let's summarize what we have done so far.
Manorama Horizon. Learning made simple.